So that allows me to record it, and people will be able to play it back later on YouTube and follow along and stop the video as they need to catch up and be easier for learning. So what I'm going to do now is I'm going to switch to my computer screen so I can demonstrate a few steps that you will have to go through in order to connect to the database and so forth. So if you don't really need to take any notes, because I'm going to upload this video later, and you can just watch it on YouTube again, and then it might be easier to just follow along. Okay, so I'm going to share now my screen here. Hopefully you can all see that.
Yeah.
Does it come across okay?
I can see it.
Very good. Great. Good morning. So what I would like to remind you of in how this Google Hangouts works, on the bottom you should see a list of icons representing everybody that has joined the call. And so if you want to make sure that the screen doesn't switch from one person to the other when somebody starts talking, you can just click on one of them and select it, like let's say the screen share that I'm providing here, so it stays on that screen unless you want it to switch. So that's just something we figured out when using this Google Hangouts, but it seems to work quite well, and even over long distances, which is very nice. So let's get started. You should have the UltraScan software installed on your computer. You can download this from our UltraScan website. Let me just go there. If you go to the ultrascan.uthsc.edu website and you click on UltraScan 3, there's a download button right here on the left, and you can jump to the software, and you can download it for Windows, Linux, and Macintosh. So when you click on one of these links, then it'll just ask you to save a setup file, which you can run. There are also installation instructions under this button here, installation. Especially if you have a Mac, you should really carefully read this, because there are some additional steps you need to go through to make sure that there's enough memory available for UltraScan and so forth. So you need to go through those steps, and similarly for Linux, it's a little bit additional work besides just running the installation program. After you installed the software, you need to register it. There's just a registration dialog that will pop up. You just fill it out and click register, and then you'll receive a link that you need to confirm in your email. And then when you do that, then you can open up the registration again and confirm your registration, and then it should work. UltraScan works in combination with a database where all the data is stored, as well as ancillary information such as buffer files and analyte descriptions and lots of other details that go along with your experiment that are helpful for the analysis. And to make use of that database, you need to tell UltraScan where to find that database. And so that's going to be the first thing I'm going to show you. In order to get to a database, you need to have a database instance already configured. And the way we have set that up is in the following way. You have, everybody has, is associated with an institution that has an analytical ultracentrifuge. Each institution then has a LIMS instance, which is one of these websites here. If you go to the LIMS 3, you see a list of institutions, and if you're in India, there is a new LIMS server now that makes the connection much faster. So you want to go down here to this one. If you're in Europe, you go to the European set of links, and here we got the Indian Institute of Science. So you want to click on that if that's where you are, and you want to make sure that you have an account here. To get an account on the system, you log in here, and you might get a warning dialog, which you do because we generate our own self-signed certificate, which is not recognized by the certificate authority that Microsoft or Firefox uses. So this is not compiled into their software. They don't know us. But you can be absolutely sure that it's just as safe as going onto your own bank or online, as long as you see that HTTPS up here. So just say I understand the risk and add an exception, and download our certificate and accept that, and then confirm that, and then you should be able to connect directly to the LIMS instance. Now, if you don't have an account yet with which you can log in, you can sign up for a new one. And it starts off by you having to fill in a captcha here to make sure that no robot is actually filling this out. And then when you enter that request, it'll ask you for your contact information, and then you submit that, and then you should check your email, and it will have a temporary password for you to get in. At that point, you can log in with your email address and your temporary password. And I'm going to log in with my account here. And after you sign in, you will see this menu right here. And at the bottom, there will be a database login info. I'm sorry, there will be a change my info button. And if you go there, you can update the password to something that you can remember. So the password that was sent to you was computer generated is probably not very memorable. So you need to change it, or you might want to change it to something that you can remember. And then you just say update, and then you log back in, and then you can use a new password. Any person logging into the LIMS has essentially no privileges on the system except to see the data that's been uploaded there by whoever is managing the LIMS database, which in this case I believe is Siddhartha. Is that correct?
Yeah.
Okay, so Siddhartha, let me just show you if you get new users at your institution. They will initially, when they register, not be privileged to use the system other than to look at their own data that's been uploaded there by whoever is administering the site or whoever is uploading the data from the analytical ultracentrifuge. To change their status so that they can actually analyze their own data and send it to supercomputers, etc., you need to go into admin info, and you need to edit user info, and you need to find the user that we want to edit. So there are a number of people. I'm not really sure. I'm going to, let's see, who do we have here? We got Akanksha on there. Let's see, Akanksha, are you in that list yet?
Yeah. The third one.
Third one. Right here. Okay, gotcha. So in this case, the user level has already been elevated to 2, which means that Akanksha already has submission privileges on this computer. If not, you can click on Edit, and only the super user can do that, in this case, Siddhartha. And then you can change the user level to a higher level, for example. And level 3 would be an administrator level, and level 4 would be super user level. That's basically what I have. And level 5 is somebody that has also access to running SQL commands directly on the database, to fix database corruptions. Like, for example, my programmer, he can go in there and investigate if there's ever an issue with the database and fix it from the website. So, yeah, go ahead.
May I ask a question? So, can I do this with my login password, or do I need an additional administrator's password?
I believe you're already an administrator. If not, I'm going to set you to be one right now. So, again, what you would do is you would go here to edit user info, and then I'm going to check where is Siddhartha?
The third from the bottom.
Third from the, okay, yeah, there we go, thanks. So, so you have user level 4, okay?
Okay.
Which is basically super user. You're in control of the whole game over there, just like I am.
Wow.
So, you're the manager. So anybody have a problem, please contact Siddhartha. Okay, so anyway, after the user level's been set, and you log in again, you will get additional permissions over here and a new functionality that allow you to submit jobs to the supercomputer for analysis. And so back to UltraScan, the first thing that we need to do is connect UltraScan and give it the information so it can log in to the same account that you're using here on the LIMS system. And for that, you need to go to database login info, right? So if you click on this button, it will give you all the credentials that you need to transfer over to UltraScan, so UltraScan can log into the same account that you're using here on the web. Okay, so basically you have two ways of accessing your data in the database. One's through the desktop GUI UltraScan program, and on the other hand, through the LIMS website. Both will talk to the same database and look at the same data. So there are two ways of accessing the data. Anyway, this is the information that you need to transfer, and you can only see that if you have user level 2. So to transfer it, you go to Edit, and then you go to Preferences in UltraScan. And under Database Preferences, you click on Change. First of all, make sure that you are actually using the database here, and it's not set to local disk. Also, the other thing you need to do first is set a master password. So if you don't have a password set already, then put in a new one, a new password, and verify it. If it already has a password, it'll show old password, and you don't need to do that again unless you want to change it. So if you have the master password set and this set to database, then you click on Database Preferences, and then we can edit the information for the Indian Institute of Science. Let me just see if I have that in here already. If not, yeah, I think I do already right here. So the first thing it wants to do when I change the database, it wants to ask me for the master password. That only needs to be entered once. And once it's entered, it is saved for the entire session. You don't ever have to enter another master password again. And it just saves it in memory and uses it every time a database connection is requested. But I already see that I have to make some changes here because the it's still linked to the old instance over on the Texas server. So I'm going to update the information and make sure it's pointing to the right server. Like, for example, here it's pointing to the Texas server, and now I need to tell it to point to the Indian server. So I'm going to change that. And then when I have all the information entered, then I click on Test Database Connectivity, and it should say the database, the connection was successful. And if it says that you're ready to go, you just click OK and save the entry. Okay? And then once it's saved, you can make it the default by double-clicking on it, or if it's the only one there, then it'll be automatically the default. So now we're done with the setup of the database, and you can quickly test the database by going to Investigator Data, and it should list the same users that we saw here a minute ago when we were trying to update the user level. So when you see that, you know, you can be sure that you have good connectivity and that your computer can connect to the local server and retrieve data from there or upload data to there. So, okay, so that's the first thing that we have. So now that we have the system working and the database connectivity established, I'm going to show you how you can upload data into the database, okay? You do that with a utility program called Import Experimental Data. And this is a place where we, number one, upload your experiments into the database, and number two, where we connect all of the details that go along with your data to the data in the relational database. So when we analyze it, we know where to find all the pertinent information that's required in order to make the correct calculations and so forth. And I'm going to go over every of those steps because it might be pretty involved here first time you go through this. So to get started, while you do have the option to work off the local disk, it turns out to be much more useful to work off the database, because if you only work from the local disk, you have no way of submitting the data to the supercomputer for analysis. That requires that you use a database. So you want to make sure this is set to database. You want to make sure that the correct investigator is listed up here. if you're an administrator, you also are allowed to connect to other users and help them basically remotely by pretending to be them, and you can select somebody else's data if you want to, you know, for example, upload data for someone else that, let's say you run the machine, but the data belongs to someone else, then you would change the investigator here to whoever the person is who owns the data before you upload the data to make sure that they'll find it in their account when they want to analyze the data later on. So if you're the technician that works on the XLA, then that's the thing that you want to do to pick the right users so that they can find their own data later. All right, and so if you already have data in the database, you could load it here from the AUC, from the UltraScan Open AUC formatted data that's in the database. I already loaded one in here just to check how it works. And I can load it again, and you can see that there are various cells and channels that have data in there. But to go through the entire process, I'm going to start from scratch and upload another data set and show you how that would work. So to import the data from the disk, you click on Import Experimental Data, and there's some workshop data here. And let me just upload this one here. This one only has a single channel. It's cell 2, channel A, and it was collected at 259 nanometers. And this is what the material was that was inside of that cell. If you have multiple cells, they would be all listed here with their cell number and their channel number and their wavelengths at which they were collected. What you will see down here is a sort of a to-do list right here in this instructions box. And this to-do list basically tells you the order in which you should proceed in committing the data to the database. So this is sort of just a little bit of a help here in case you're not so familiar yet. Later on, you probably won't ever look at this again. But for right now, it helps to follow this. So the first thing you're supposed to do is modify the run ID. So if it says demo 1 will lock and you really don't like that and you want to say this is DNA lysozyme, this is a little bit more descriptive, you might want to put that in there instead. This is a mixture out of DNA and lysozyme, so I'm going to type that in there instead. So now I've done the first step. Now the next step is to edit the run information. So I go into Edit Run Information, and here, again, I want to make sure that the investigator is set correctly. We're on the database. And then we have the run ID listed here. And then we can put a more verbose label in here, you know, something like that, whatever. The name, the run ID, cannot contain spaces or special characters because that actually is a directory name. So the directory name, you know, shouldn't have any spaces in it, and it also shouldn't have any control characters in it or something like that that has a special meaning to an operating system. So you just want to use alphanumeric characters here. And over here you can make a more verbose description that has also spaces in it and whatnot, and commas, whatever you like. This will be a short listing of the contents of the data of the experiment that you can see in the database when you pull down the listing later. Next, you need to associate the data with a project. Okay, so what is a project? So a project is essentially a lab notebook in which you keep track of what you're doing with this experiment. Okay, what are the goals? What are the molecules involved? What's the experimental design? How fast are you going to spin it? What kind of buffer are you using? So you basically keep track of pertinent details that relate to your experiment. It's a really nice thing to have, especially if you collaborate with other users. I keep saying that, you know, there are so many projects that are worked on with collaborators that come back years later and say, well, we finally solved the structure, now we want to publish. Or what about that AUC data you collected 2 years ago? You know, do you still have that? And then I go in there and I go, oh my God, well, fortunately I have this project. And the notebook is directly associated with my data and has all the details and all the information that I need in order to write the paper. Okay, so always keep that. You can make a new project by just clicking here, New Project, and then giving it a name. And then what you can do is you can fill out all these different things. So here's a section for filling out the goals of the experiment, where you describe what it is that you're trying to figure out. Here you have a section where you can put the molecules in, the peptide sequences, all of those details. You can discuss the purity of the molecule. You know, how much of the material can you come up with? You know, how much concentration can we have in order to study this? You know, talk something about the buffers. What kind of, how much salt do you have to have present? Do you require reductants? You know, what is the buffer that you can use? Is it transparent in the UV, or does it absorb? And if so, at what wavelengths? Those kind of details can be entered here because they're all relevant towards the experimental design that you're going to come up later. How much salt can you include? You know, what are the questions for the AUC? What do you want to learn? Do you want to see if it has mass action? Do you want to see what the size distribution is? Do you want to know if the molecule is dimerizing? What exactly is it that you're trying to figure out? So the user puts all of those details in there, and then when you have all of those details at hand, you can come up with an experimental design where you put in, you know, the speed of the experiment, how long you want to run it, what temperature, what rotor do you want to use, you know, what concentrations do you want to measure, how much material do you want to put in there, etc., etc. And then you might put some notes in there, like maybe for, you know, only store the sample at 4 degrees, never freeze it, don't add any glycerol, or, you know, it has to have reductant present. Those kinds of things you can put in here. So once you have all of those details written down, then you go back to General and you just say Save Project. And then that project will be listed in your project list, and you can just accept it and associate it with your experimental data. So then in the future, when you look at your experiment, you can always find the project that belongs to it and read through all the details. Okay, the next thing you need to do is you need to go and pick the lab and the rotor that was used here. So a few words about this. So I think you only, well, there is this demo lab in here that we can use that, but normally you would just put IISC. That's, you have a lab there, a central facility that has that machine. So if that one was used, then you would be you would select this, and then you would add a rotor, or you would pick a calibration. So there are already a few default calibrations in there. Why do we need a calibration, a rotor calibration? Let me just tell you what this is. So typically you have an 8-hole rotor or a 4-hole rotor, an AN50 or an AN60. And what these rotors do, when you spin them at higher speeds, they actually stretch. Okay? And as they stretch, the position of your meniscus and every data point inside of your cell sort of moves out towards the outside of the rotor, because due to the stretching, it just gets translocated. And with that, all of the particles will be in a higher centrifugal force field. And when we solve the Lamb equation to fit the data, we need to have boundary conditions. And the boundary conditions are the meniscus position, the bottom of the cell position, and also the fact that no concentration can be outside those 2 points. So all the data has to be within the bottom and the top of the cell. And if they're not, then that means your sample is leaking or something like that, and we can't model it anymore. So as long as the boundary conditions are satisfied, and you have conservation of mass, you can use the Lamb equation to model this experiment. And we need to know exactly what those positions are. Now, when the rotor stretches, then these positions will change as you accelerate the rotor. And rather than measuring this, which is often not possible because you can't see where the bottom of the cell is, usually the absorbance there gets very high, and you don't really get a good signal from the bottom. So instead what we do is we measure the centerpieces by scanning them on a high-resolution scanner and get very precise geometry information about each type of centerpiece that is available. And then we put those in the database, and together with the rotor, we know how much it stretches because we have a calibration for each rotor. We can then calculate precisely where the bottom of the cell is, and we don't need to measure it. And so by using those boundary conditions, now of course the meniscus we can fit, so we'll fit that one, and then the bottom of the cell is fixed based on our previous measurements. And so we don't need to fit the bottom, because that would be, fitting two boundary conditions would be a little bit too problematic, so we don't do it. Anyway, you can add your own calibration to it by going to Add New Rotor. And what you really need to do in this case is you need to run a calibration for that new rotor that you add. And so if this is an AN50 or an AN60, then there are some parameters that are pre-given. For example, the cell center is 6.5 centimeters by design. It's made out of titanium by Beckman, and it can go up to 60,000 RPM. The AN50 can go up to 50,000 RPM. And you can give each rotor a name and a serial number. And then for each rotor, you can also add calibrations. And calibrations are essentially experiments where you scan an edge of a centerpiece in intensity mode for every speed that the machine can do, like 1,000, 2,000, 3,000, 4,000, all the way up to 60,000. And you get a measurement of how much the edge moves. And there's a program in UltraScan that lets you do this calibration very easily once you have the data. You just load the calibration data into that program, and you define where the edges are, and then the program will go and extract those data out and calculate a statistical average over all of the speeds and all of the cells that you've scanned, or cell edges that you can scan, and it will use that information to fit the stretching to a second-order polynomial to get the stretching factor. And these polynomial, the first and the second polynomial coefficients are listed here. Then you can also enter an omega squared t, which is the total integral, or total number of revolutions, or something like that, that will indicate the age of the rotor at the time of the calibration. And then you can name the calibration, and it will be listed here with a date that you can then use. So let's say you have an AN60 rotor, and we're going to use the default one that we've calibrated here, and you just use that calibration. It's probably close enough, but you can make your own to be more precise. Then you can pick that, and it will put in the relevant stretching factors, and you can accept that and associate that with your experiment. It will then look at the speed and fit that polynomial and look up what is the value at 42,000, and it'll use that as a stretching factor and add that to every point. And over here you would basically pick whoever is the person that ran the machine. And if there are new ones, you got to give them permission to also run the XLA. You do that in that Edit Info tab that we looked at before, Siddhartha. So you can give other people technician privileges for the machine. Once you selected that data, it will automatically detect what type of an experiment it was, like a velocity, their equilibrium, diffusion, buoyancy, calibration, or other experiments. So if it's not picking up the right one, you can correct that here. It should also pick out automatically whether it was an absorbance or intensity or interference or fluorescence or multi-wavelengths or whatever. And it'll pick those things up, and it'll put this in here as well. Then you can add some comments like maybe cell 3 leaked, or the buffer had too high absorbance or something like that. You put your comments in there so you can go back later and see what went wrong, if in case anything went wrong. But anyway, after you fill all of that run information out, you just say accept. And then you see there are only two more things to do here to get your data into the database. One of them is to select a centerpiece and to select a solution. So again, as I mentioned before, we have scanned in every centerpiece geometry. So we have those in here, and you just pick whatever centerpiece you were using. This was a standard EPON 2-channel centerpiece from Beckman. So we're going to pick that. And then we have to pick a solution. Now, a solution is essentially whatever you put in there, in that cell. And the solution consists out of a buffer and one or more analytes. And the buffer, of course, is needed because you need to know how much density and viscosity correction needs to be taken care of when you do the standard calculations for S and D. So we need to know the density and the viscosity of the buffer. And fortunately, we have buffer tables for a lot of different components listed in here. And you can create yourself a buffer. Let's say it's a tris buffer with 20 millimolar tris. You put in 20, and then it'll add 20 millimolar tris, and maybe there's some sodium chloride in there. So we find that as well. That would be here. So maybe I'll put in 150 millimolar sodium chloride, and then maybe there's some EDTA in there. Let's find EDTA. And maybe there's 0.5 millimolar EDTA. And now we have a 150 millimolar sodium chloride buffer in tris. And maybe it was pH 0.0. Okay, so that's my buffer, and it has these things in there, and I just say save. Okay, now it gets added to my list up here. I have those components in that buffer, and it automatically calculates what the viscosity and the density correction is for this particular composition. And that number is used during every analysis of every data set that's associated with this buffer, so that the answer that you get back will be corrected for 20 degrees Celsius in water. So you get the already corrected S values in, so you can always compare one experiment against the other. Yes, go ahead. Go ahead, Siddhartha.
Yeah, does it correct for the pH also? Because your buffer is pH 8 and here it says pH 7.
So this pH 8 I just typed in the listing here. So I really should put in I really should type in 8, right? It doesn't correct for the pH because the pH generally doesn't affect the viscosity or density. So this is just something to keep track of for the user what pH this experiment was done in. So you're quite correct. I should have updated that. If I did it down here, you know, I could also do it here. And then of course I need to resave the buffer, right? And that's what it just asked me to do after I hit enter here. So let me just update it. There we go. Another thing you can do is, yeah, go ahead.
I'm having a problem here. I'm not able to save my buffer.
You have a problem with what?
Yeah, it gives me an error message when I say it to save buffer.
Okay, do you have the database set up correctly yet?
Yeah, I did that.
Okay, and you're trying to save the buffer, and it says what?
Error updating buffer in the database. My SQL no rows returned.
Okay, yeah, the very first time when you do that and there's nothing in there, it just says, I can't find any data in there, so I can't pull anything up and show it to you. So you just click OK. The first time you save a buffer, it should be, that error should go away.
Okay.
So can you save the buffer now?
I'll try it. What exactly should I do? I did okay, but still when I say save buffer,
Can you show your screen so I can take a look at that?
okay. How do I do it?
So there is a little, if you go over to the left of your screen and you touch on the left screen of the left corner of the screen,
Yeah.
then a little bar should come up, and at the top there is like a green icon with a white arrow on it, and if you click on that, then there's screen share, and then you can share your screen, and I can take a look at that.
Can you see it?
Yes, I can. All right, so you double click on that phosphate buffer 20 millimolar in the upper left. Double click on that.
Okay.
And then click accept.
And then click what?
Accept.
Accept.
Actually, I want a different buffer.
I'm sorry?
This is the one which I used previously, but I was trying to enter a new one which is not getting saved.
Okay, let's go this. I can't see your screen. There we go. All right, let's try this again. Can you share your screen one more time?
Oh, yeah. Okay.
Okay, so click on select buffer.
I think it stopped responding.
Are you clicking on the screen or on your window that you're sharing? It's not responding, you say?
Now it's working. Can you see it?
Yeah, click on select buffer. I don't see it actually shown on the screen.
Okay. So I'm on the buffer database portal.
Can you repeat that?
Can you see it now? The buffer management area.
No, you may have to share your entire screen rather than just a single window, because right now it's not pointing to anything.
Okay.
Can you share your entire screen? That should be listed in the list of screen shares.
Oh, it's there. Okay. I'm getting different options. Can you see the
Okay, so
buffer?
yeah, okay, so uh, so let's stick here at your buffer. All right. So I don't see any buffer saved yet. So let's create a buffer here.
Okay.
So just pick something, okay, out of the
Okay.
list. Click on item to select, and then pick something. You know, it doesn't really matter what. You can make another one later. Just pick something. Put in like
Okay.
20 millimolar, for example.
Okay.
Okay. So now click on save buffer.
Yeah, I did.
Oh yeah, you got to put in a name too. Sorry. So yeah, right there. Put in a name, and then just click save. So what does it say now?
The same error updating buffer in the database. No rows returned.
Okay, well then it sounds like your database isn't correctly set up. Which what is your user name in the database?
Akanksha.
Let me just take a look here. Okay, so you do have permissions to connect to it. Are you on a Mac or on a Windows system?
Windows.
Okay. Let's see. Let me see if I can connect to your account right here. So I see your phosphate buffer listed in there, and it pulls it out just fine.
Yeah.
And if I go into, let's say I make another one here, like let's say I make a TE buffer. It adds it just fine.
Okay.
So, and this is from here, so it sounds almost like you have still some network connection over there, some network issue. Make sure that when you set up your, if you look at my screen here for a second, when you set up your database, make sure that these details are entered correctly, okay? It almost sounds like there may be a connection error, or maybe some of the details, the password or whatever, is not correctly set up. And you might want to close the application completely down and start it up again and see if it works then, okay? But and if you continue to have problems, send me an email offline and we'll take another look at that, okay?
Yeah, thanks.
I'm going to go back to myself now.
Boris?
Yes?
Can I have a question?
Sure.
Okay, so when I prepare buffer, I normally titrate trees with hydrochloric acid, but this could also influence density, right?
Hydrochloric acid?
Yes.
Yeah, I would think a little bit. It probably isn't very much. How much do you put in there? Just a few drops for pHing, or?
Well, actually, I don't know, but when I use 50 millimolar trees, so I put some, I don't know, 1 milliliter.
Yeah, God, it will be very, very minor, that contribution. I wouldn't worry
Okay.
about it. I think that's pretty much captured inside of the tris. I think the tris that's listed here is probably more or less made for like a pH 8 or somewhere in that range. So unless you're very far off with that, I wouldn't worry about it, okay?
Okay, thank
This
you.
is very, very minor contribution. Anyway, let's get back to the solutions. I wanted to add a buffer here. So we need to pick the buffer. I haven't created one. I haven't saved it yet. So let me just go back here and save it. So we had 20 millimolar tris, and we had some sodium chloride in there. Where is it? There it is.
There.
150 millimolar NaCl. And then we put some EDT in there too. And then we're gonna save this. Now I'm getting that same error you have. What is going on here? No, it sounds like there is something more serious going on that we need to look at. I noticed the same error now when I try to click on the same buffer.
Yeah.
Some little glitch there that we have in the database that needs to be fixed. We'll take a look at that. It's definitely something I can reproduce here. So Akanksha, so thanks for pointing that out because I'm seeing the same problem.
Okay.
Let me pick the one that we already have here. We'll definitely get that fixed. So in this case, it doesn't really matter, you know, what we have for this particular experiment. I'm just making something up for demo purposes anyway. But right now, I picked this BSA buffer that I had, and so it's listed up here. And I also have to put in an analyte. So I go to Add Analyte, and you can either enter a new one or you can use a pre-existing one from that list. If you want to enter a new analyte, you just click here, New Analyte, and you change the name. So let's say lysozyme, for example. And then you can put in the sequence for it. So you put in, you know, whatever the sequence is, and we'll just take those, see if it cleaned them out, the invalid characters that I typed in. But anyway, so we have a sequence, and it will tell you what the molecular weight is, how many residues are in there, what the extinction coefficient is, and what the partial specific volume is. And once you entered that, you just say Save Analyte, and then hopefully we don't get an error here. There's still a write permission error. So I think that database has some problem right now in its configuration, and we need to take a look at that. That's unfortunate. So this is newly set up, and we need to debug it, I guess. But that can be solved fairly easily. We'll get that straightened out today. So I'm just going to pick BSA because that's already in the database. So then all the analytes that I would have in my solution would be listed here. And then we would give that solution a name and save the solution. This is probably going to fail too here, as I'm trying to save things to the database. Well, this one did get saved. That's strange. Well, maybe not. Let's see. Of course, now I'm going to India, and this is a much longer connection from here, so it takes a little bit longer. So now I have the test solution in here, which is based on BSA buffer and the BSA protein. So if I click on this, if I double click on this, then I can use this for my database. I mean, for my experiment, and associate that solution with this particular channel. And then I would just click on Accept, and it would grab that and associate that with my data. So I'm not really sure why those two tables are giving us trouble here, but we'll get that sorted out. And now that we have a solution associated with our experiment here in this particular channel, and we also selected a centerpiece, there is essentially nothing left to do over here, and we can save the data into the database by clicking on the Save button. Now, curiously, it's allowing me to save this. So I'm not really sure what's going on here, but at least we can get some data in. So the other thing is that if you have multiple channels here, and let's say they all have the same stuff in them, and they all use the same centerpieces, you only have to fill out the first one, and then you could say Apply All, and it will copy that information to all the other channels. So you don't have to do it for every one of them. And then you could save. So anyway, our data is now in the database, and we can start working with it. Okay, so you can close this. So now what we want to do is we want to get an idea of the S-value range that we might have to fit in on the supercomputer. So for that, we go to well, first we need to edit the data. Sorry, we need to edit the data to tell it basically where the meniscus is and where the data range is. And so we pick it. Now we have two experiments in the database. One of them is this DNA lysozyme. Oops, it looks like it didn't save it. Let me load the other data set so we can edit that. Yeah, this one here. Let's see if they're in there. So there may be some. Yeah, there is some database issue that we need to solve here before we can actually proceed. I'm just stumped right now why this isn't working. Because we tested it previously, and but something has changed since the last time that I used this. So maybe we need to take a look and make sure that MySQL server is running properly on that system. But we'll get that sorted out. Well, I'll have Gary, our programmer, check into that today, so that should work tomorrow. Well, that's unfortunate. I can't even load a data set now. No, it says there's no files in there. Let me see if I can see it in the data manager, because I thought something got uploaded. If I scan the data, it basically scans all the data that's in the database and all the data that I have locally stored on my disk, and it compares them, and it checks whether they're identical or whether they're different, and where I have data stored, so I can find it. So what I want to know right now is, do these data in the database, do they show up correctly under this manager? And if not, then that might give us a clue as to what's going on. I had the impression that it was uploaded. Now I don't know why it doesn't let me download it again. Has anybody else used the database at all yet?
I tried this in Europe and it functioned normally.
And what happened?
It's okay. No problems. No issues.
Okay. Gary, do you have some insights on what might be going on here? You need to unmute your microphone, Gary. Can't hear you. Gary? Waiting for Gary to unmute his microphone so we can hear what he's saying. Anyway, while we're waiting for Gary, we now have a listing of all the experiments that are on disk in a brown color. And then in the database, it should be listed in a different color. In this case, green, if it's both on the disk and in the database. And what this shows me is that there is AUC data stored in the database that is identical to what I have locally stored on my hard drive. So in that sense, it should have pulled it up, and I'm not sure why we can't access it right now. But I'm sure Gary will look into that and let us know what the problem is. I see Gary is joining the Hangout, but he has his microphone muted, so we can't hear what he's saying. He apparently can't figure out how to make the microphone work. So we'll wait. We'll wait for him to figure this out. But there are clearly data sets here, and we've already analyzed data, so I'm not sure why today we can't see it in some of the other programs. I'm going to try this one more time here. So Gary says that he's been trying it, but his microphone isn't working, so for some reason he cannot provide audio.
And when you try some different database, for example from Europe, does it work or no?
When you use it in Europe, you're using a different database.
Yeah, that's right.
So I'm not really sure what the issue is with the LIM server in India. We've just set that up recently, and for some reason it's not working correctly today. So Gary wants to know what exactly the problem is. So Gary, what's happening is when I go into edit and try to load the data, it says there are no AUC files available, even though they're listed there. And if I scan for the data in the data manager, they show up just fine, and they match with the data that I have on the disk, so they show up in green. Also, when we're trying to save a buffer, it gives us an error saying no rows returned, no MySQL rows returned, even though there is stuff already stored in the database when you're trying to save it. And then we can't save it, and you have to click OK, and nothing is saved. And the same is true for analytes, and apparently also when you upload data, they don't get correctly saved. So I'm not really sure what's going on with the database, but maybe you can take a look at this and figure this out. We can also pick it up later and look at it in more detail. So unfortunately, I don't really know what else I can do right now to show you this, because no matter which data set I'm trying to load, it gives me this error. There were no files in the form of star.auc found in the specified directory, and it's trying to load it from the database. And then the same error occurs when users in India are trying to access data. So I'm not really sure what to do next here to make this work. And clearly was there before and accessible before, because I've already analyzed some of the data. I'm going to see if I can load it into another program. Now it says no edit children exist for selected run demo 1 intensity. The run will be hidden. This is on the this is on FEMatch when I'm trying to load data from the IISC database under my name. So that's not working right now. So I apologize that we can't get any further here. What I could do is switch over to my database and show you how things work there. And then meanwhile, maybe Gary can take a look at the India system and get that to work. And so this is what I'm going to do now. I'm going to switch over to my database here so we can continue to work on and show you how to analyze and upload data. So what I'm going to do now is I'm going to quickly upload another data set. So I go into import experimental data, I go into my workshop data, and maybe load up this run, demo 1 block, and I'm going to change this to DNA2 lysozyme. This is a run I don't have in the database yet with that name. Then I'm going to change the, well, I'm sorry, now I'm going to have to edit the run information. So here I select the rotor calibration. So we have our own AN60 rotor here with our serial number. And we have a calibration for this. I'm going to accept this. And then we have a label for this. So this is a DNA lysozyme data set. And we're going to select the project that goes with this, maybe demo 1 here. And once we have all these details in there, I'm going to pick an operator and accept the data. And then I still have to pick the solution and the centerpiece. So I'll pick the centerpiece here, and now I still need to do the solution. And here I pick whatever buffer is in there. I already have a mixture here, DNA lysozyme. And this one has a DNA fragment, the lysozyme, and the buffer, and I'm going to just say accept, and now it associates this particular solution with this particular experiment, and I can save it. So now we're basically back to where I was before when the Indian server failed, and I can go back into edit to edit this data. So I'm loading, and it should be in chronological order with the latest one at the top. So I'm going to pick this, and it'll show me the data here on the edit screen. And so the first thing I need to do here is to pick the meniscus, which is this green button highlighted here. If I made a mistake, I can click on it again and do this over again. So basically what I do here is I'll just push down the control button on my keyboard, and I drag the mouse right over that position, which looks like it could be the meniscus. And I'll let it go right there. Next, I have to specify the data range. And I start on the left, again holding down the control button, and move my mouse to the left corner of my data set, and then to the right corner of my data set. And then it'll grab what's in the middle and use that as the accessible data range. Next, I pick the plateau region. That's the region where most scans have a stable plateau. So you can see that the first scan, has a long plateau region that extends all the way from here to there, while the last scan has only a plateau region maybe from here to there, and then it already starts curving up from the back diffusion. So we want to be in that region where all scans have a stable plateau, or most scans. If you have more scans in the experiment than I do, then you may have no more stable plateau, and then you just look for the largest number that have a stable plateau and go to that position, and that would be somewhere around here. So just click on this. If you have spikes in the data where the lamp didn't fire, you can just click on remove spikes, and it'll get rid of those. And then when you have all of this done, you click on Save Edit Profile. And at that point, you can give it another name, because you can have multiple edit profiles in case you wanted to check out the effect on the analysis of, let's say, deleting various scans, or maybe using different limits or whatever. You could try all of that out and then give each edit profile a different name. Or by default, if you just want to work with one edit profile, which is probably the easiest, you could just accept the default, which is a timestamp. So in this case, it's 2015, 07 July, 09 is the day, and then 1431 is the time. And I think this is UTC, so Universal Time Zone. So it's using that, and I click OK. And now my edit is saved, and I can close this, and I can start analysis. And to start the analysis, I usually start with a time derivative and load my data set into the time derivative method. And that gives me a very rough estimate of where the sedimentation range is, where we have signal, okay? So in this case, it looks like there's a bump over here and another bump over here, and it pretty much stops at about 8S, okay? So we have something here between 0.5 to maybe 8S, okay? So that would be the range that I would want to evaluate and trying to find the signal for the components that are in this mixture. If you want, you can save it, and if you save it, it writes a report and saves it in the database, which you can access later. If you go here and you click on reports, then here's a I'm still in the wrong database, so I got to switch over to let's see here. I got to go to this one right here. Log in. This is mine. So I go to the reports, and then the lysozyme 2 is alphabetically ordered, I think. Let's see, where is it? DNA 2 lysozyme, that's where it is. So, and then you get a link for it, and when you click on it, it loads up the report, and you see here on the time derivative, it saved, for example, the spreadsheet that goes with it, It saves the plot that we just looked at. It gives you an analysis report and a plot of the scans, and then some of these other plots that were generated in the analysis. So you have a record of it in the database now that you can access through the website. All right, now that we know what the range is that we need to fit, 0.5s to 9 or 8, I think it was, we can go and submit a job by clicking on Queue Setup. And so we pick our experiment from the database and then use the cell or channel that we want to analyze right here, and we add it to the queue. And now it's going to ask me if I wanted to use the last edit that I made, and since we only have one, that's a perfectly good choice, or if I want to make individual manual selections in case I have more than one. And so in this case, I just use the latest edit. And then I need to decide what analysis method I want to use. So I want to start up with the 2DSA analysis and go from 0.5 to 8S. And then this is the resolution I'm going to use, and we can leave that at 64. That's a pretty good default resolution. You might want to increase that a little bit if you have a much larger S-value range. And then we want to fit the time invariant noise. And then we want to pick a cluster. And here you can see what the wait times are for the various clusters and how many jobs are running and how many are queued. And it looks like Alamo doesn't have anything queued. So why don't we pick that and submit there. And now that we're submitted the job, we can go into queue status down here, and we can see the job and see what it's doing. So there are some jobs running right now from some other people, and we got to scroll down until we find the one that's ours. It's right here, and we are currently queued. And we're already finished. So that only took 6 seconds on a supercomputer to analyze. So we can now go and look at the result by going to Velocity and Finite Element Model Viewer. So when I'm here, I just load the experiment, and then there should be a model under Load Model right here. It's not there yet. It's not uploaded yet. Let me see what happened. That was DNA 2 lysozyme. We have all kinds of problems with the database today. What's going on? Well, we need to wait until it's actually disappeared from this list. So if it's still listed in that list, that means it hasn't had a chance to upload it into the database. So we need to wait until this is cleared. This updates every 30 seconds, so we may have to wait another 30 seconds or a minute before this goes away. It's not there yet. Gary, why does it say job status request reports job is running? Even though it's completed. So there's still some problem with the queue viewer not reporting the correct job status, because I know this job should be finished by now. It never takes more than six seconds. So there's apparently some problem with this particular job here right now. Sorry, we're running into all kinds of unexpected problems today. But the model appeared, so let's not worry about it. Let's load up the model. And there's a noise file associated with it for the time invariant noise. We're going to load that as well, and then we can simulate it. And you can see in the simulation that we got a very good fit. We have very random residuals, and the red line, which represents the model that we calculated, nicely traces the experimental data in yellow So we know that our model matches our experimental data quite nice, and we have a low RMSD value. So everything looks good. Now we can also visualize the results, like let's say in 3D by clicking on the 3D plot here. And you see, we see two groups of major species. There's the lysozyme down here, and there's the DNA up there. And we can spread this out a little bit to make it a little bit more visible. It's here. My keyboard is a little slow, so, but anyway, you can enhance this figure so you can see what's going on. Basically, we have something here between around 0.2s, and then there's something around 0.5, I mean 5s and 2s. This is 10 to minus 12. So here's our DNA, which is a little bit more extended and anisotropic, and here's our lysozyme, which is a little bit more globular, so it is lower on the frictional ratio range. So we're telling apart two molecules that are basically different shapes and different size, and we can tell them apart. Now, it returns two peaks right now, and that may be because of our selection of our limits, but later on when we refine the data, that should go into a single spot, and I'll show you how that works. So the next refinement step is to actually fit the meniscus. Okay, and for that we go back over here, and we're going to say Q setup, and we pick that run again, same channel, add it to the queue. Again, use the latest edit for this, send it to 2DSA, and use our same limits again. And in this case, fit the time invariant noise again, but this time we also fit the radially invariant noise, and we fit the meniscus. And submit it again to Lone Star, or no, to Alamo. So well, let's send it there. And then we can follow along what happens when we go to Q status. And where's our job? Oh, this is way at the end here. So we're waiting, we're sitting in the queue right now on Alamo, and we're waiting until we get a turn. It said there were three jobs pending. And it looks like we're behind this person here, so we may have to wait a little while until we get through. There's another job in front of us. So another option that we have is to submit the job to another cluster if you don't want to wait that long. So it looks like Comet is working fairly quickly. So let me delete our job here. Of course, you can let it sit. Eventually, it'll get in. But you can also delete a job. And then you can submit it elsewhere. And for that, we go back here. I'll go through this exercise one more time. Okay, 0.5, and then 8. And the frictional ratio range will leave the same. That's fine. We're going to do the time invariant noise, the radially invariant noise, and the meniscus fit with 10 grid points. And I'll send it to, let's say, let's try Lone Star. Let's go back to the queue status, and hopefully we can find our job here. So here we are, queued on Lone Star. Let's see how long it takes to get a turn there. Looks like other people are starting to use Lone Star as well. So anyway, here you see a list of all the jobs that are currently underway, being run using UltraScan. Most of them are queued, some of them are running. I see most computers are nice and busy. So anyway, you're sharing this system with others. The nice thing is you can pile a whole bunch of jobs up at once and just let them sit in the queue until they get their turn, and it usually goes fairly quickly. And then you can get all of the results back at once. So that's kind of nice, but right now it's kind of bad because I wanted to show you and I didn't want to wait at all. But it's very busy today for some reason. So, but now it says here our job is running, which is strange because here it still says it's queued. But eventually it will probably work. Are there any questions while we're waiting?
Boris, this is Siddhartha here. I have no questions because I have no data. It's the students who have it.
Yeah. Well, no, that's perfectly fine. And there will be a little bit of a learning curve as you all go through this and play around with it and practice with it. But don't worry about it. You know, if you forget something, we can always repeat this. And if you have questions or problems, let us know, and then we'll help you remotely to get through them until you become very familiar with it. In which case, the analysis goes very quickly, and you don't even have to think about this. So, but as you get started with it and start learning the system, feel free to let me know, call me, and ask me questions. One of the things I wanted to point out to you is another website here that may be helpful. If you go to home, I think UltraScan 3, let's see, there's some documentation here, or tutorials. I think you want to take a look at those. There's a sedimentation velocity analysis flowchart, and that basically has all the steps I'm going through documented.
Okay.
And so you might want to read that too as a guide to help you through the refinement process to get to the final answer. And then also in each program there's extensive help, so you'll always find a help button in there. And if you click on this, it'll load up the help documentation, and it'll document a lot of the things that that I've been talking about. And if there's anything missing, you know, let us know, and we'll be happy to help you out again. So please make use of that. Don't waste any time trying to figure something out which is not clear to you. Just let us know, and we'll be happy to help you. And Gary, normally his microphone works. Also, is very helpful if you ask him for questions with problems related to the computer or to the software. If there's some issues that are not working with the database, please let us know so that we can address it quickly. And we'll definitely deal with this issue with the LIMS database in India. We'll get that sorted out today. I'm almost certain that that will be fixed very rapidly, and then you can use the system too. So let's see if anything came back here. You go back. Let's see where we are. Looks like a lot of jobs are in the queue right now. A lot of jobs, so it takes a while to load it up. It's a queue status. What's going on here? We're not getting the queue status back. Well, let's see if our job is finished. I'm going to take a look at it by looking at the models, but no, there are no meniscus fit models back yet. So I'm not sure what the issue is, but now the queue has refreshed here, so let's see where our job is. Job status reports, oh, it's updating and it was aborted, so something didn't work out. I'm not really sure what happened here. We need to take another look at that. So anyway, I think I'm going to let you get started with uploading your data. We will send each one of you an email, let you know when the LIMS server is back up. It apparently needs a little bit of maintenance here. And then you can get started with submitting some data to the database and maybe submitting a job to the supercomputer and analyzing it. And then please let us know if you have any questions or problems with it, and then we'd be happy to address those. Okay?
Okay, Boris, thanks a lot. I think we'll get started. And, you know, we'll go through the steps that you've shown up to this point and move on using the help pages that you have on the website.
Okay, that sounds
good. Hopefully, you know, we get, yeah. Thanks a lot.
Yeah, you're welcome. And then please be in touch with any questions, okay?
Yeah.
Alrighty. Bye-bye, everybody.
Okay. Bye.
Bye bye.